Hi mom, hi classmate, I am Leanat. So I'm going to tackle the intro of Fibonacci heap. Introduction of Fibonacci heap. A Fibonacci heap is a data structure that consists of a collection of trees which follow mean heap or max heap property. We have already discussed mean heap and max heap property in the heap data structure article. These two properties are the characteristic of the trees present on Fibonacci heap. So a Fibonacci heap is a consist of collection of trees through the main heap and max heap. So we have already discussed the max and the main heap. Max heap property is the root node niya or the value of the node is larger than the other nodes. While sa main heap property naman is a smaller root node or the value than the other nodes. So itong two property ng trees is siya ang mag-present sa Fibonacci heap. In a Fibonacci heap, a node can have more than two children or no children at all. Also, it has more efficient heap operation than that supported with the binomial and binary heap. So sa Fibonacci heap, a node can have more than two children or no children at all. So here, pwede maging marami ang children ng node ng Fibonacci heap. The Fibonacci heap is called a Fibonacci heap because the trees are constructed in a way such that a tree of order n has at least fn plus nodes in it, where fn plus 2 is the n plus 2, the Fibonacci number. The Fibonacci heap is called a Fibonacci heap because the trees are constructed in a way such that are tree of order n. So yung n, meaning yan is number of node, has at least fn plus 2 nodes in it, where fn plus 2 is the n plus 2 Fibonacci number. So that number of node, i-add mo siya by 2, then hanapin mo yung sagot sa Fibonacci number. So this is the example. So for example, 3 plus 2 equal to 5. Yung 3 is the node number. Then i-add natin siya sa 2, magiging equal to 5. Then hahanapin natin dito sa list ng Fibonacci number yung 5. So if 5 equal to 5, ibig sabihin 5 node lang ang meron. So makikita nyo dito sa example ng peak, yung pinakamaliit na value sa least root is the 3. Siya yung ating mean. Then lahat ng root list value nito is small compared to their children na malaki yung value. Tulad ng 18, 52, 38, 30, 26, 46, etc. Properties of Fibonacci heap. Important properties of Fibonacci heap are: number 1, it is a set of mean heap ordered trees, i.e. the parent is always smaller than the children. Number 2, a pointer is maintained at the minimum element node. Number 3, it consists of a set of marked nodes, decrease key operation. Number 4, the trees within a Fibonacci heap are under but rooted. Number 1, dapat mas malaki ang value ng parents than their children. So number 2, dapat mayroong isang pointer na nagtuturo sa node na naglaman ng pinakamaliit na elemento. Sa number 3, yung mga marked node ay isang mechanism na ginagamit sa decrease key operation or pagbabawas ng value ng isang node. Sa number 4, the trees within a Fibonacci heap are under but rooted. So that's all about. Thank you.
Hello everyone, my name is Nur Eliza Yuso. My topic is all about memory representation of the nodes in a Fibonacci heap. So, what is it all about? A Fibonacci heap's memory representation involves a collection of nodes interconnected through pointers, forming a structure optimized for efficient heap operations. So, this is how the Fibonacci heap structure. So, the node structure. Each node contains the following information. So, we have the key, degree, parent, child, left sibling, right sibling, and mark. So, in the key, the value associated with the node. This is the primary element used for comparisons in the heap. So, in the degree, the number of the children in this node has. We have the parent, a pointer to the parent node, and null if the node is a root. Child, a pointer to one of its children, null if it has no children. We have the left sibling, a pointer to its left sibling in the circular doubly linked list of its sibling. Right sibling, a pointer to its right sibling in the circular doubly linked list of its siblings. And the last, we have the mark, a Boolean flag indicating whether the node has lost a child, since it became a child of another node. So this is used to optimize the decreased key operation. So we have here, there are two main advantages of using a circular doubly linked list. Deleting a node from the tree takes 0 incremented one time. So in deleting a node from circular doubly linked list takes constant time. This is because you need to adjust the pointer of the node's immediate neighbors. You don't need to traverse the list to find the node's position. So in the concatenation of the two lists takes time. Joining two circular doubly linked lists also takes constant time. You simply need to rewire the pointers at the end of the two lists to link them together. So here no traversal is necessary. So we have here the example of on how to insert an element. So as you can see here, the minimum point 3. So since you know our topic is Fibonacci heap, so dito naman sa baba makikita natin na insert yung 21. So ganito na yung itsura.
So, good day to each and everyone, especially to you, ma'am. My name is Margaret Garigan, and my topic for today is all about Fibonacci heap. So, first, let us understand the algorithm of Fibonacci heap in insertion. There are operations in Fibonacci heap, and we have the insertion. From the word itself, it means we're adding new nodes sa heap while still maintaining yung kanyang structures and properties. Now, let's break down bawat parts ng algorithm. First is we have the initialization rather. Yung degree x, ito yung nagsiset ng degree para sa new node natin na x to 0. Yung degree ng bawat node, they represent as a number of children. Yung px equals nil, naman they set the parent of the new node na x to nil. This indicate that it has no parent node or root node. Next is child x, which is quite obvious na this set a new node which is yung node x to nil, indicating wala pa value yung child node natin. Then, left x, this set the left sibling para sa new node natin, which is x, and this is only node na nakakonect sa kanyang root list. Same with left x, the right x ay obviously nagsiset ng right sibling para sa new node natin na x. And itong node na to ay nakakonect sa root node. Then, last is mark x equals false. This will mark our new node na x to false. Why? Because it will indicate whether yung node na yun nawala ng child during the last cascading cut. Cascading cut is something that arranged in a series or stages. Now moving on to the root list integration. Concatenate the root list containing x with root list h. This link the new node na x into sa root list ng Fibonacci heap, which identify as h, meaning it connect a new node doon sa mga existing root list pala rather. And this will form a circular list. Next is minimum update. You can see that in here, if min h equals to nil or key that is lesser than key min h, then min h equals to key. So if yung heap h daw natin is empty, then a new node h ang magiging minimum node. Or if yung key daw natin na new node na, or if yung key daw ng new node natin which is x with the current minimum node ng min h ay i-compare silang dalawa. If yung key ng x is smaller, then ito na yung bagong minimum node. And lastly is the node count update, which is nh equals nh plus 1. So this part will only increment or add by 1 sa new node ng heap natin or h. Moving on to the inserting a node into an already existing heap, follow the step below. So these are the steps when inserting a node sa existing heap na. First is create a new node for the element. So this step involves creating new data structure to represent yung element na gusto mo i-insert. This node actually contain mga data value and meron din ito mga pointers to its parents and children. So basically, it's like a tree-based heap. Next step is check if the heap is empty. So this step actually determines whether yung heap already contains an element or not. If yung heap is empty, it means there are no existing node para i-compare or to place doon sa structure. Next is, if the heap is empty, set the new node as a root node and mark it min. So when the heap is empty daw, yung new node ang magiging root node sa heap. And this will mark as min because in min heap, dapat yung root node ang naghahawak ng smallest value. Lastly is, else insert the node into the root list and update min. If yung heap is not empty naman, then we need to find the correct position para sa new node na ipapasok sa heap structure. Yung root list, this refers to the array representation ng heap, and yung new node ay ini-insert sa end ng array. Then we also need to update the min since we added new node, need din natin to i-check if yung value niya ay smaller ba sa current minimum value. If it is, then the minimum value is updated and yung new node ang magre-reflect as a new value. This step actually ensures na yung heap property where yung mga parents node ay nagiging smaller pa or lesser than or equal pa sa kanilang child node. So, dapat nag-remain valid ito sa ating heap structure. So, that's all. Thank you for.
Find mean. So, paano ba natin ma-find si mean? It's like, the minimum element is always given by the mean pointer. So, dito sa example nito, then, as you can see, si mean pointer, gina-point niya si 3, which is, siya yung, minimum element. That's all.
Good morning everyone, my name is Amir Bianti and I'll be discussing the extract mean and union in Fibonacci. So as for the union, when we say union, it is a union of two Fibonacci heaps. It has two following steps, which is the first one is concatenate the roots of both the heaps. The second one is to update the mean by selecting a minimum key from the new root list. So in here we're gonna unite all the root nodes like this one. The next one is extract mean. So in this operation, the node with the minimum value is removed from the heap and the tree is readjusted. So para maintindihan, we're gonna perform an extract mean operation heap. So the first one, we're gonna remove the mean nodes, or here is the tree. Then next we're gonna make its child nodes, or we're gonna add the root nodes in the this node or the roots, which is the 18, 52 and 38. So the next one, we will create an array of size 4 and map the degree of the next root with the array list. So in here the maximum degree in the tree is 3. So in here 23 and 7 have the same degree, so you will unite them. When we say degree, it is the number of nodes that is inside the root. Next, 7 again. 7 and 17 have the same degree, so we will gonna unite them as well. So next, 7 and 24 have the same degree, so we're gonna unite them again. So the last step is we will gonna map the remaining nodes or all the nodes.
Good day everyone. Assalamualaikum to each and every one of you. Moving on to our topic, which is deleting a node, let's go back again or recap what is Fibonacci heap. So again, a Fibonacci heap is a tree-based data structure which consists of a collection of trees with minimum heap or maximum heap property. Its operations are more efficient in terms of time complexity than those of its similar data structure like binomial heap and binary heap. Now, we will discuss two of its important operations. The first one is a decrease key, which is decrease the value of the key to any lower value, and the second one is delete a node. So now we are talking or tackling about the delete a node or deleting a node. That delete a node, it deletes the given node. So we have here the specific explanation about it. So deleting a node is the process makes use of decrease key and extract minimum operations. The following steps are followed for deleting a node. But the deletion process in a Fibonacci heap leverages two key operations, decrease key and extract minimum. So here's the step-by-step explanation. First one, let k be the node to be deleted. It means we are going to put on a value of a k to be the one to be deleted. So first step is we are going to identify the node to be deleted, which is the value of k. Locate the node k in the heap that needs to be removed. So it means we're going to remove the node of a k that we're going to remove. Second step is apply decrease key operations to decrease the value of k to the lowest possible value. For example, if the value of the k is 3, then we are going to decrease it for the lowest possible value. So we can make it 1 or 2 or even 0. So decrease the operations to negative. Use the decrease key operation. Again, we are going to decrease the key operations to reduce the key value of the node k to the lowest possible value, typically. So this makes the case the smallest key in the heap. So again, it will make the node or the key node to be the smallest key in the heap, ensuring it becomes the minimum node or minimum in the Fibonacci heap. So the third step is apply extract minimum operations to remove this node. So it means we are going to extract minimum operation to remove the node. After setting the key of k to decrease, apply the extract minimum operations. Then, the extract minimum process removes the node with the minimum key, which is now the k. So we got the value of k after we reduce it or decreased it. So, any children of K are detached and merged into the root list during consolidation. It means any children or any other node of K are detached and merged into the root list during consolidation. So, there is a question here. For example, why do we decrease K first? The answer is that the Fibonacci heap does not have a direct delete operations. Again, the Fibonacci heap does not have a direct delete operations. The decrease key operation is used to move the node to the top of the heap structure by making it the smallest element. Again, ladies and gentlemen, the Fibonacci heap, take note this the Fibonacci heap does not have a direct delete operation. Does not have a delete operation. The decrease key operation is used to move the node to the top of the heap structure by making it the smallest element. Yes. So again, question, why use extract min or extract minimum? So the extract minimum operation is designed to efficiently remove the smallest node. So, ibig sabihin, the extract minimum from the word extract itself, it extract the smallest node or efficiently remove the smallest node. So, by combining this with the decrease key operations, we effectively implement the delete operations. So, that's how we implement or that's how we use the delete node or deleting a node. In complexities, we have decrease key is equals to 0, open and close parenthesis 1, or amortized. And the extract minimum, 0, log n, or 0, open, log n, parenthesis, amortized. So the total deletion of 0, log n, amortize. This method ensures that deletion is efficient while maintaining the properties of the Fibonacci heap. So again, I had said the reason of why we are using a deleting node. It is to maintain, or this method ensures that deletion is efficient while maintaining the properties of the Fibonacci heap.
Good morning, everyone, especially to you, ma'am. I am Margaret Regan, and my topic for today is all about complexity of the Fibonacci heap. First is insertion. In here, obviously, wait a minute. So this is insertion from the top of the table. So in here, obviously, we add new element to the main heap. The time complexity is O log n because in the worst case, yung new element I needed nasa root ito siya. And because of this, it requires traversal of the height ng heap. So the table is actually incorrect. It's stated as O1. But this is only true kapag yung heap are not maintained as binary tree. Next is find min. In here, we are retrieving yung mga minimum elements coming from the min heap. This operation takes constant time. So, O1 because yung minimum elements or mababang value ng elements ay dapat as a root ng ating heap. Next is union. Here we are combining two min heap into a single min heap. This operation typically has a time complexity of O1 where it's ON pala, where yung N ay yung total number ng elements sa both heaps. The table O1 is actually incorrect kaya yung pag-merging ng heap ay hindi constant time operation or always nagaganap. Next is extract min. We are removing yung minimum element na galing sa min heap. Ang time complexity nito is O log n because after na removing root, yung magiging last element naman ito ang magiging root. Kaya need siya i-move. And with this, the heap structure needed the heapified down para ma-restore yung min heap property. This actually requires traversal ng heap height. Next is decrease key. Here, we reduce the value ng specific element sa min heap. This operation has a time complexity of O1 because the elements need to bubble up or ipataas para sa correct position. And lastly is delete node. From the word itself, meaning we are removing a specific node na galing sa min heap. This has a time complexity of O log n. Kaya typically it involves finding a node then ginaswap ito sa mga last element. Then they are heapifying it. So heapifying means basically it's like reshaping yung binary tree into a heap structure. So in the late mode, they are heapifying it para ma-restore yung min heap property. Now, we'll move on to the Fibonacci heap application. So first is to improve the asymptotic running time of Dijkstra's algorithm. So ang Dijkstra's, di ba, this is used to find the shortest path in the weight graph. Well, using Fibonacci heap, yung overall time complexity ng Dijkstra's algorithm ay nag-i-improve kaya dis-enhance yung mga beneficial dense graph, making the Fibonacci heap as a powerful choice para sa mga application tulad ng route planning at network optimization. So that's all. Thank you.